Hello everybody. Welcome to my complex analysis quote-unquote class. I'm going to stipulate I'm not a teacher. I'm not even... I am teaching myself this class and the subject. It is, as you can see, 3:45 a.m. So it is late. But I wanted to start a little bit of a series where I kind of just go over complex analysis. What the subject is. And these first videos will be basically the basics of complex numbers. So we're going to say that this is unit 0. The basics of complex numbers. This is video 1, or lesson 0.1. Imaginary numbers. Now there is a whole story behind the imaginary number. The imaginary number came from... The imaginary numbers can be traced back to Girolamo Cardano. Girolamo Cardano is credited as the person who solved the cubic. Basically, when a was equal to x to the third, bx squared, bx, cx plus d equals 0, he could figure out what x was equal to. He is credited to solve it. That can be traced back to the discovery of how to solve the depressed cubic. The depressed cubic was first found, or first known to be found, by a man named Scipione. I believe I'm spelling that right. Nope. Scipione de Ferro. Blech. Who discovered the solution to what is known as the depressed cubic, which is basically, instead of this full cubic, it is a cubic without the x squared part. He gave this to his student, gives to a student. His name is slipping my mind. Who then challenged a man named Niccolo Tartaglia. Who then discovered the same way to solve the depressed cubic as him. This was given to the student on his deathbed. He had kept it secret his whole life. Niccolo Tartaglia. Okay. Tartaglia. Whatever. Figured this out by doing the same way that we figured out how to solve this, which was by squaring the square. It was by completing the square. Where if we took the expression to complete the square, which basically, if given a quadratic as such, like this, what you do is you can take a square besides x, and then a rectangle make two rectangles with sides 11/2 and x. And we have that if we have a completed figure, the area of this whole thing equal to 4. So what we do is we then add a piece of value here, because once again, I'm shade in the parts that exist already. That's terrible shading, but we know that those parts exist. So, to complete the square, since it's just a little L shape, we have to add this box, which is 11 to 11/2. And because, it's an equality, we have to add this to this side. Square. So, now we have that completed the cube. It's a very complex thing that requires kind of 3D visualizations, which I don't have. There's a great Veritasium video that goes into the whole thing in depth. But basically, he uncovered the formula. He then derived a formula for the depressed cubic. And there's a lot more to the story that Veritasium goes into, but this is basically the formula. Taking the equation x cubed equals 15x plus 4, where we have x to the third equals cx plus d will then eventually simplify down to the cube root of 2 plus negative 1/21 plus cube root 2 minus root negative 1/21. And thus, it was deemed unsolvable. But when looked at it, we can take this and manipulate some things. If we separate these, and we simplify this down, I forgot to add that. It was found out that eventually the root negative ones would cancel, and thus the equation became solvable. Once again, Veritasium goes into this equation a lot more. I'm just using it as an example. This root negative 1, notated by Euler as I, as it was called, imaginary. So now the I equals root negative 1. This is a property. It is very important. It is the defining feature of complex numbers. We know this. We can do this. So I to the 1 is equal to I to the 1 is equal to root negative 1. I I squared is equal to negative 1 I to the third is equal to I squared times I, or negative 1 times root negative 1, so it equals negative I. I to the fourth is equal to I squared times I squared equals negative 1 equals 1. And we can define this, and a fun one, I to the fifth can be separated into I to the fourth, I, which then equals 1 times I. So since 4 equals 1, we can split this up. We can take any large number, and we can easily find what its value is, as the remainder of when you divide 294, which we can say mod. Mod tells us the value of the first number, and when we divide it by this number, what the remainder is. Two. So we can rewrite this expression as I to the 4, I to the 4, I to the 4, dot dot dot, 70 more times. And then an I to the 2, and since all of these are equal to 1, it is equal to I to the 2, which is equal to negative 1. So a very simple unit into the discovery of it, and of course what I represents. In the next lesson, 0.2, I will go over over basic complex numbers. Over the standard notation of imaginary numbers, the properties of adding and subtracting complex numbers, and the properties of multiplying and dividing complex numbers. I have assigned 10 problems, split into 3 sections, each with 4. These are basic quadratics. Good review. For just good review, especially for what's next, which is quadratics with imaginary. Actually, that's wrong. Quadratics with complex answers, which tell you, since I haven't technically gone over it, when a complex number is notated with alpha plus beta I, alpha is the real part, so we would write, so like, a complex number would be 5 plus 2i. Within this, you'll see why we kind of get that a lot, I think, but you can't simplify this any further, so. And then 9 through 12, I just want you to solve for z, which is the typical variable used for complex numbers, which is just integers raised to I. I raised to integers, I think is a better way to put that. I will solve these at the beginning of the next lesson. Yeah. Thanks for watching. Got a bit ranty, but that's just because I kind of need to be. Because this was more so the discovery of imaginary numbers, less so what they are. What they are is this.